Usually when we sit down to go through a stack, all the research papers, the clinical trials, we're kind of looking for the catch.
Yeah, especially in nutrition. There always seems to be a catch.
There's always a hidden cost. It's like a law of nature that if it tastes amazing, it's probably, metabolically speaking, trying to kill you.
It is the sad reality of the modern food environment, isn't it? Delicious usually means inflammatory or high glycemic or just empty calorie.
Right. But today, the documents we're looking at, they seem to argue the exact opposite. We've got this comprehensive report, the clinical and metabolic implications of D-allulose. And honestly, if I hadn't read the data myself, I'd think this was a late-night infomercial pitch.
It does have that too good to be true ring to it at first.
It really does. I mean, we are talking about a substance that is, for all intents and purposes, sugar. It looks like it bakes like it even caramelizes. But the claim here is that instead of wrecking your metabolic health, it might. It might actually be hacking it.
And hacking is absolutely the right word. This isn't just about a low-calorie substitute. We're talking about a molecule that interacts with your biology in a way that is, well, strikingly similar to some of the most advanced weight loss drugs on the market.
That's the headline for me. That's what jumped out. We've seen low-cal sweeteners forever. Zero sugar sodas, that's old news. The real story here is that this specific sugar seems to trigger the exact same hormonal systems as Ozempic and Wegovy, that GLP-1 connection.
That is the game changer. And the mission for this deep dive is to figure out if this really is the holy grail or dream sugar that metabolic medicine has been searching for, or if we're just looking at another fad.
So let's just jump right in. We're talking about D-allulose, sometimes called D-sucrose, and the notes keep calling it a rare sugar. I want to start there. What makes a sugar rare?
Well, it's rare in terms of its quantity in nature, not its existence. Nature absolutely makes allulose. If you eat a dried fig or some raisins, even maple syrup, you're eating D-allulose. But, and this is the key, you're getting microscopic amounts. You couldn't possibly extract enough from figs to sweeten your coffee.
Got it. So commercially, it has to be synthesized. But chemically, this is what threw me. The diagrams call it a C3 epimer of fructose.
I know. C3 epimer sounds like a droid from Star Wars.
It does. So translate that for us. What does that actually mean?
Think of it like a key in a slightly miscut key. Fructose is the sugar in fruit. We all know it. Allulose is almost identical. Same atoms, same weight. But at one specific spot, the third carbon position, hence C3, a single oxygen-hydrogen group is flipped.
So it's like putting a left-handed glove on your right hand.
That's a perfect analogy. It looks like a glove, it feels like a glove, but it just doesn't fit. And in this case, the glove is your body's digestive enzymes. They try to grab onto it to break it down, but because of that one little flip, they just can't get a grip.
Which brings us to this concept from the report that I just love, the ghost visitor.
It's a great visual. It explains the metabolism perfectly.
Okay, so walk us through it. I eat something made with allulose. It goes down to my small intestine. And this is where it gets weird, right? Because it's not like fiber, which just passes through. Allulose actually gets absorbed.
Correct. And that's a crucial distinction. About 70 to 80% of the allulose you eat passes right through the intestinal wall and into your bloodstream. It enters the house.
So it is technically in my blood. My blood sugar, or blood allulose, I guess, is now elevated.
Yes, but this is where the ghost part comes in. It enters the house, it wanders around the living room, looks at the pictures, but it doesn't touch anything. It can't be used for fuel. Your body can't turn it into fat. It just circulates, metabolically inert.
It's a polite ghost.
Very polite. And very quickly, your kidneys see this molecule hanging around and say, hey, we can't use this, and they just filter out. Within 24 to 48 hours, pretty much all of it is gone, excreted in your urine.
It came, it saw, and left. And that explains the calorie count, right? Something like 0.4 calories per gram.
Exactly. About a tenth of regular sugar. But if the story stopped there, if it was just another passive low-calorie sweetener, we wouldn't be doing a deep dive on it.
Right. We're here because the ghost, while it's wandering around, is actually pressing some buttons.
The very specific and very powerful buttons.
Let's get into the heart of this report, the GLP-1 connection. This is the part that feels like science fiction. We know GLP-1 is the satiety hormone. It's what tells your brain, I'm full. How is a ghost sugar with no calories triggering a satiety hormone?
So the report breaks this down into two totally separate mechanisms. One is chemical, a lock and key, and the other is, well, it's basically physics. It's mechanical.
Okay, let's start with the chemical one, the lock and key.
Right. So deep in your gut lining are these specialized sensor cells, are called L cells. Their job is to taste what's passing by. Normally, glucose uses a transporter called SGLT1 to get their attention. Allulose, though, it ignores that door.
It's got a VIP entrance.
It does. It uses a different transporter called GLUT5. And when allulose binds to that GLUT5 transporter on the L cell, it's like a specific molecular handshake that tells the cell, release GLP-1 now.
And we know it's not just the sweetness, because that's a common criticism of sweeteners.
That's the key finding. The researchers showed that if you block the sweet taste receptors, the effect still happens. But if you block that GLUT5 transporter, the effect stops dead. The cell isn't tasting sweet. It's recognizing the specific shape of the allulose molecule.
That's wild. Your gut is literally smarter than your tongue. But what about the second mechanism, the piezo-1 channel? This sounds like it belongs in an engineering manual.
It really does. Piezo-1 is what's called a mechanosensor. It doesn't sense chemicals. It senses physical pressure. It senses stretch.
How does a sugar stretch a cell?
It's really subtle. Remember how we said allulose is absorbed, but it's a bit slower than glucose? Because it hangs around in the intestine a bit longer, it exerts an osmotic effect. It pulls a little bit of water from your body into the gut.
Okay, so it slightly increases the volume of fluid in there.
Precisely. And that causes what's called luminal distension. It physically stretches the wall of the intestine just a tiny, tiny bit. And those L cells, they have these piezo-1 channels embedded in their surface. When the cell membrane gets stretched, the channel pops open.
Like a trap door.
Exactly like a trapdoor. And a rush of calcium ions floods into the cell. That calcium surge is the other trigger that screams, release GLP-1.
That is incredible. So you're using the physics of water retention to flip a hormonal switch that controls your appetite.
It's an incredibly elegant system. And that GLP-1 signal doesn't just stay in the gut. It activates the vagus nerve, which sends a message straight to your brain to signal satiety, and another message to your liver to improve insulin sensitivity.
It's a true biological hack. You're tricking the body into thinking it's eaten just by using this one rare sugar.
Which is why we need to think of it less as a sweetener and more as a functional food. It has a job to do.
Okay, but devil's advocate. This all sounds great in theory, but does it work in people? The report had that sucrose load experiment, which felt very real world.
Yeah, this was a pivotal study. They took 30 healthy people and gave them a 50-gram hit of pure sucrose.
That's a big soda. A sugar bomb?
A total sugar bomb. Your blood glucose would normally spike like a rocket. But in the test group, they simply added 10 grams of allulose on top of the 50 grams of sugar.
So they actually ate more stuff total.
Yes. And counterintuitively, their blood sugar spike was significantly blunted. It was reduced by about 12 milligrams per deciliter. The allulose acted like a buffer.
A sugar buffer. I like that.
And it seems there's a magic ratio. About 1 part allulose to 5 parts sugar seems to be the sweet spot for blunting that spike. It seems to inhibit some of the enzymes that break down carbs.
That's a huge takeaway for anyone who bakes. You don't have to go 100% all in. You can just blend it with regular sugar and still get a real benefit.
Precisely. You're putting a governor on the engine.
So, speaking of baking, let's talk comparisons. How does allulose stack up against, say, erythritol, the keto darling?
Well, erythritol has 2 main issues in the kitchen. One, it has that weird cooling effect in your mouth.
Great, like a mint without the mint flavor.
It's odd in a brownie.
Very odd. And 2, it doesn't brown. It won't do the Maillard reaction, so your cookies stay pale and crunchy. Allulose, because it's a real monosaccharide, it behaves like sugar. It caramelizes, it browns, it gives you that chew.
Okay, so it wins on taste and texture, but what about the GLP-1 side?
Erythritol does stimulate some GLP-1, but the data suggests you need a really high dose, like 50 grams, to get a strong effect. And stevia is even more inconsistent. Some studies show it does nothing for satiety hormones.
So allulose is kind of the clear winner on all fronts right now.
It's definitely hitting all the marks.
Which brings me to this idea of synergy. We're living in the age of Ozempic and these GLP-1 drugs. Could allulose be a companion to those? This is such a fascinating area of research. Think about it. The drugs work by flooding your system with a synthetic version of the hormone. Allulose works by stimulating your body to make its own natural GLP-1.
So you're keeping your own internal machinery running.
That's the hypothesis. Imagine someone tapering off those medications. The biggest fear is the rebound weight gain because the hunger comes roaring back.
Right.
But what if you have a dietary strategy? Using allulose to keep those natural satiety signals firing, maybe that transition becomes a lot smoother.
A dietary safety net makes a lot of sense, but there's always a but. We have to issue the bathroom warning.
Yes. The GI distress. We cannot skip this part.
That osmotic effect, the water being pulled into the gut. If you pull in too much, that has a predictable outcome.
A very predictable and unpleasant outcome. Bloating, gas, and a wonderful word, borborygmus.
Which is just the scientific term for loud, embarrassing stomach growling.
The kind you don't want in a quiet meeting. The report is very clear on the thresholds, and people need to know the math here.
Please, let's save everyone some trouble.
For a single sitting, the max dose before you risk issues is about 0.4 grams per kilogram of body weight.
Okay, so for a 70-kilo person, that's
28 grams.
28 grams, about 2 tablespoons. Now, if you bake a batch of cookies and swap the sugar one for one, and then you eat 3 or 4 of them, you could easily blow past that limit.
And you'll know it.
You will absolutely know it. The daily limit is higher, about 0.9 grams per kilogram. So you can have more throughout the day. You just can't have it all at once.
The report used 2 spoons ice cream as an example of smart dosing.
Yeah, it's a great case study. They use about 6 grams of allulose per serving. It's enough to trigger the GLP-1 sensors and act as a sugar buffer, but it's way below the distress threshold. They're using it as a tool, not just a bulk sweetener.
That's the real shift in thinking, isn't it? It's a bioactive compound, not just fake sugar.
Exactly.
So before we wrap, I want to leave everyone with the most, I think, provocative idea in this whole stack of research. It's about our gut bacteria and evolution.
Ah, the ALZ gene. Yes.
Yeah.
So we established that humans can't metabolize allulose, but it turns out most of our gut bacteria can't either.
Right. The report says only about 15% of people carry gut microbes that have the ALC gene, which is the specific genetic code needed to eat allulose.
For the other 85% of us, it's a total metabolic free ride. The bacteria just ignore it.
For now. But that brings up a huge evolutionary question. If we all start eating allulose in everything,
Our coffee, our baked goods, everything.
we are creating a massive evolutionary pressure in our gut. We're providing a new food source. Will our microbiome adapt? Will more bacteria figure out how to switch on that gene?
And if they do,
Then this zero-calorie sugar is no longer zero calorie. Your bacteria start eating it, producing byproducts, maybe a lot more gas. The ghost is no longer a ghost.
so we might just be in a temporary golden window, the free ride era of allulose.
Biology's never static.
Yeah.
We're hacking the system today, but the system always tries to hack back.
That is a fascinating and slightly terrifying thought to end on. Enjoy it while it lasts. Well, there you have it. The secret life of D-allulose. Not just a sweetener, but a rare sugar that acts like a metabolic modulator, making a pretty decent cookie in the process.
Just remember the 1-to-5 ratio. And please, watch your dose.
Start slow, check your labels, and maybe don't eat the entire batch of brownies in one sitting. Thanks for diving deep with us.
Stay healthy, everyone.